Assalamu alaikum, guys. Hello. Today I would like to talk about this book's one chapter. I will talk about probability and information theory, and I will explain based on the slides, and it will be not as detailed as in book, so therefore I highly recommend you to check out the book. You can actually get free e-version of the book if you visit deeplearningbook.org website. So let's start now with explanation. Okay. So I think my screen is visible to you. So let's talk probability and information theory. It is based on the chapter 3 of Deep Learning book by Ian Goodfellow. The book was published in 2016, which might be quite old, but still relevant. Let's talk about probability mass function. Actually, what is probability? Probability is a mathematical framework used for representing uncertain statements. As you know, there are in machine learning, in classical computer science, many branches of the computer science deals with exactly deterministic and certain uh, entities. But machine learning deals with uncertain quantities and sometimes with stochastic quantities. Stochastic means non-deterministic quantities. And for example, if we want to find the probability of flipping a coin, we will use probability mass function. So in order to use this probability mass function to find the probability, it should follow these three rules. If the event uh, follows these three rules, we can use this probability mass function to find the probability of the variable. Before explaining each of the rule, I want to explain you that variables can be two types: discrete or continuous. Discrete numbers is discrete variables. It's not only integers. Discrete variables is variables which are countable, which we count. They have certain limit. They have certain lengths. Whereas the continuous variables are infinite. They are infinite. The actual real numbers, they start from 0 to infinity. We consider them as continuous variables. The probability mass function is used to find probability in the discrete variables. So the domain of probability must be the set of all possible states of x. If we will take flipping a coin, that there is only two states, tail and head. And second rule is that an impossible event has probability 0 and no state can be less probable than that. Okay, that works. Likewise, an event that is guaranteed to happen has probability 1 and no state can have a greater chance of occurring. It's also true for flipping a coin. The third one is that we refer to this property as being normalized. That means if we sum all the probabilities of the outcome, it will give us number 1. So in case of flipping a coin, it is uniformly distributed, and that k is the length of outcome. In terms of flipping a coin, k is equal to 2. That it has only it may have a tail or head. If we have two events occurring at the same time, if I flip two coins at the same time simultaneously, my k, this k variable, will be equal to 4. because if I use these two coins to flip simultaneously, the outcome may be tail tail, or tail head, or head head, or head tail. In that case, k is equal to 4, and xi is equal to tail head, or tail tail, etc. That's about probability mass function. So let's talk about probability density function. So this mass function, probability mass function, deals with discrete numbers, but they cannot deal with continuous values. Why? Assume we have outputs from 0 to infinity, and if I say what is probability of number 1 occurring in this range from 0 to infinity, so we cannot say certain numbers here because the probability of that number is equal to 0 actually. So we cannot, if we cannot find the actual probability, we can create some how can I say, we can create some abstraction out of that, and we can find the probability density function. So we can say that if it is uniformly distributed, that what is probability of number 3 parameterized with a and b. So if we give the range a and b where b is higher than a, we can find the probability of x in this range. It wouldn't be the actual probability, but it is sort of abstraction, and that one is calculated by 1 divided by b minus a. And there are also three statements, three rules. If the probability of the event, if the event follows these three rules, we can use this density function. Okay, computing marginal probability with the sum rule. So as far as I understood, that marginal probability is required to find the probability of just one subset of one, just to find the probability of one subset of the big complex event, instead of focusing on the whole probability. Mm, this one is for discrete variables. This one 3.4 is for continuous variables. Based on that, we can find the marginal probability. Let's talk about conditional probability. Conditional probability is the most interested. So many people are interested in this one because we're always interested in the probabilities of one event occurring after a second event. For example, here we can say the probability of y event, given that there is x event, we can calculate the probability of y and x divided by probability of x alone. And we can calculate only this conditional probability if the probability x happened. If it will never happen, we cannot calculate this conditional probability. And there is chain rule of probability that we can represent set of probabilities events by by this function, by this equation, by this function. So we can decompose the distribution into conditional distributions. We can decompose this probability into the many conditional distributions. Independence. If there is two events, x and y, if probability of x multiplied to the probability of y is the same as the probability of both, we can say that they are independent. There's also conditional independence. So the random variables x and y are conditionally independent given a random variable z if the conditional probability distribution over x and y factorizes in this way for every value of z. The conditional independence that if we represent the x given by z and probability of y given by z independently, and if the result of this right side of the equation is equal to the left side, they are independent. Let's talk about expectation. Expectation, it's a bit general. I'm sure you have heard about mean value, about average, about mode. Expectation for discrete variables is indeed mean or average value. Meanwhile, the expected value or expectation for the continuous variable is the integration of this formula function. That's all about expectation, not too complex. Variance and covariance. Variance is that tells us how different the given variable from the expected variable. It shows us the difference between one random variable compared to the mean, compared to expected value. So there is official term, official explanation. The variance gives a measure of how much the values of a function of a random variable x vary as we sample different values of x from its probability distribution. It means that if variance is small, if variance of x is small, it means that x close to the expected value. If variance of x is high, it means there is big distance between expected value and the x variable. I think you have heard about standard deviation. Standard deviation is nothing but square root of variance. So the square root of variance gives us the standard deviation. And why we need standard deviation is that standard deviation does the same, but the unit of standard deviation is the same as the unit of the x variable. We will come to standard deviation in random distribution, in normal distribution, I mean. So what is covariance? Covariance gives some sense of how much two values are linearly related to each other. So it gives us how likely two variables are connected linearly, but it cannot give us non-linearity. If for example, if two variables has non-linear connection, they are their covariance will be equal to 0, but they will be depend on each other. So yeah, maybe I messed up. So is that what I want to say is that covariance and dependency is two distinct concepts. For example, independent, if two variables are independent, they have zero covariance. And two variables can have non-zero covariance are dependent. As I said, that covariance cannot show us the nonlinear connection of two variables. It means that if covariance is equal to zero, it's not necessarily means that they are independent. That's the point. Bernoulli distribution. Bernoulli distribution is distribution for uh, discrete numbers. Bernoulli and multinolli distribution. Bernoulli is for binary. Multinolli is for many more discrete values. For Bernoulli distributions is phi given x is equal to phi. When x is equal to 0, 1 minus phi. If we want to find x in the x, we can use this formula to find that one. The expected value is this phi, that it is mean, and the variance is phi times 1 minus phi. It's all about Bernoulli distribution. For Bernoulli distribution, it's just we can say this is Bernoulli distribution. We have only two binary. Yeah, we have only two solutions, two outcomes, and this one is multinolly distribution. We have countable outcomes, but their probability is different. That's how multinolly distribution looks like. Next, we will talk about Gaussian distribution. Gaussian distribution is very common and in practice. So Gaussian distribution is used for continuous variables. This uh, this symbol stands for standard deviation. So there is graph. Why Gaussian distribution? We call it normal distribution. There is also one axiom, like not axiom. There is one statement that saying that many distributions we wish to model are truly close to being normal distributions. Another name for Gaussian distribution is that it is bell curve. It looks like bell curve, and if you look closely, the x is maximum. So the probability of x is maximum in the zero. Mean value is zero, and the standard deviation is that how far the distance of the between expected value and the given x. For example, if x equal to minus 1.5, the standard deviation is the distance between it to the expected value. That about Gaussian distribution. If you want to cover more, just read this deep learning. Go to this website and go to lecture slides, this link, and just read from here. Okay, we covered Gaussian distribution. Next, multivariate Gaussian. That formula. Normal distribution generalizes to Rn, in which case it is known as a multivariate normal distribution. So maybe it's not clear enough. And okay, so there are different types of distribution also. So actually, if you wonder what is actually distribution, distribution is how the outcome are spread. For example, distribution, for example, if you make survey of like 10 people, and if you collect their age, and the distribution is of this set of discrete number, is frequency of each number, each value is occurring. There are also exponential distribution, Laplace, and Dirac. Their shape is a bit different. From here we can see the red one is exponential. There is sharp between 0 and 1. There is very sharp curve, and in negative way it's equal to 0, whereas the Laplace is extension of the exponential distribution. It also goes to negative side, it also goes to positive side. And the Dirac distribution looks like this. It means that the distribution at the value 0 is equal to infinity, whereas on other place it equal to 0. There is also empirical distribution. It says that Dirac is one version of empirical distribution. I have no comment more to say about this. So we can represent distribution as combination of distribution. For example, if you look to this graph, it has 3 components from left to right. The first component has isotropic covariance matrix, meaning that it has the same amount of variance in each direction. The second one has a diagonal covariance matrix, meaning it has control the variance separated along each axis aligned direction. And yeah, there are three components, and there is logistic sigmoid. So logistic sigmoid is a function where if we give high minus number, big number, it will go to it will be close to 0. If we give a very high positive number, it will go to 1, close to 1, and their range is between 1 and 0. Soft plus. In soft plus, we can see that in negative it is close to 0, but if in positive it grows. And there is also softmax. Okay, Bayes rule. Bayes rule is used, as I mentioned previously, to find maybe degree of belief. For example, if I say, for example, what is the probability of person has cancer, given that his medical test results, we can calculate the probability based on this rule, that px is what's probability actual generally of people having a cancer. We calculate that one. It is called prior probability. And if we calculate p probability of the what is the probability of the medical results given that you have a cancer, that's likelihood, you calculate that one. And if we find p of y, which means that what is it is summation of both events. In our case, that what is probability of person having a cancer, and what is probability of person that not having a cancer, and we sum of these two values and we will find p of y. Bias rule is also used in spam filtering. It's a classical example of spam filtering. So I can probably give you good example here. Just a moment. Okay, I think there is no good example. I think I didn't save. Okay, here is example. Okay, now we have, so P of E, in this case of E is means the Y. It is the total probability of observing the evidence under all possible hypotheses. That's usefulness of bias rule. What is information theory? So we use information theory to quantify how much information this probability has, or certain probability has. The, the information theory saying that events which are likely to occur, or events which has higher probability of occurring or higher chance of not occurring, has less information than the probability uh, of of variables, of probability of rare variables. And one example the book giving is that it gives two examples. For example, it says the says that it says, where was the sentence? Just a moment. For example, if there is sentence, the sun rose this morning. So sun usually rose this morning, right? I mean, like sun usually uh, what rose every morning. So the probability of this action is very high. And information theory is saying that this sentence, this probability is informative and unnecessary to send. But if there is probability of rare event, for example, if there is message saying that there was a solar eclipse this morning, is very informative because it contains the probability of rare events, of rare outcome. So like solar eclipse is not the thing that usually happens. And yeah, generally information theory is like tells us whether this probability or whether this event has information or doesn't have information. And In case of Bernoulli variable, Bernoulli means binary, terms of binary values. It means that, for example, sun can rose, sun may not rose, right? In terms of z, we have only two outcomes, and that we can say that if the probability is high, is equal to 1, the information it containing is equal to 0, means it doesn't have information to be shared, to be sent. If probability of, for example, of sun rising is equal to 0, it also has 0 information. If probability is equal to 0.5, it has highest maximum amount of information, and this is how the information shape look like in Bernoulli distribution. So this KL divergence, I couldn't give enough. I cannot give enough explanation. Sorry for that. You can definitely go to the chapter and read more. So, and there is also one thing to cover: directed and indirected model. As I understood that there are probabilities or events which are depend on another event. So from this case, we can see that event E depends on C, while C depends on A and B event. So D arrives from B, B arrives from A. In terms of Z, we can decompose the probability of this sequence of events into this probability, conditional probability, and we can represent them as graphs. And graphs may have direction and may not have a direction. And this is undirected model. And this is formula for undirected model. So that is a general explanation of chapter 3. I'm repeating one more time. So you can freely go to this website, and click this link and read the electronic version of that chapter. Another thing I highly recommend you to do is to go to YouTube, and there is Deep Learning Chapter 3 Probability presented by Pierre Duke, and it is under the channel of Alyona Krychkova. It is 6 years old. It was published 6 years old, but you may find more practical example, more practical explanation of that chapter. So basically, that's all about today. I hope you got somehow good overview of what is chapter 3 and what is probability and what is information theory. Yeah, mostly they are theoretical and they are not good applicable in practice, and sometimes you may forget them, but it is always good practice to learn to review this kind of fundamental principles of machine learning of AI. That's it for today. If you like the video, press thumb up, subscribe, write comments. That's all for today, guys, and see you next time. Bye bye.